Hello everybody, in this video I will be introducing onshape-to-robot, which is a tool I've been working on those previous years. The motivation is to be able to produce automatically URDF or SDF robot formats directly from the CAD software. So on one hand, when you design a robot, we used to of course draw it in a CAD software, which is usually a constraint geometry software solver, like SolidWorks, CATIA, Autodesk Inventor, or Onshape. And on the other hand, we have the robot description formats. So it can be URDF, SDF, MGCF for Mujoko. And basically, they are all XML describing the robot architecture. So the position of the joints, the dynamics, the mass, inertia. But all this information you want to have to simulate the robots, but also to operate it, because you can do some kinematic requests, like getting the position of a frame in respect to another, knowing the position of the joint, of course, etc. So all those information are already in the CAD. So this process can be almost automated entirely, and this is the topic of this video and of onshape-to-robots tool. So first, why Onshape? Onshape is a constraint geometry software, just like the others. It's software as a service. You only need a web browser if you want to use it. It can be used for free, especially if you have educational background, you have educational account with a free license. And most of all, there is an API. So Onshape-to-robot is a Python API requesting the parts from Onshape, retrieving your assembly, retrieving your parts, and creating the URDF from those requests. And this is why it can work, actually. So we can design a robot in Onshape, or import a robot in Onshape, assign all the proper materials, do an assembly. So here we are looking at some very simple quadruped that is based on small low-cost dynamic cell servo. And we can, with using onshape-to-robot script, which is actually a Python script, you can automatically import this assembly, create the URDF, and then throw this URDF in bullet, suppose, and then you can play with your robots and use your robots in simulation environments seamlessly. So you don't have other efforts to do, except all the configuration of onshape-to-robots that we will discuss now. So just as a quick overview of the features now, onshape-to-robot supports prismatic and revolute joints, can export to URDF and SDF files. MGCF is not yet supported today. Dynamics, it can be computed by Onshape, because in Onshape all parts have materials that you can assign, or you can override those manually. There is possibility to create pure shape approximation, especially using OpenScad, but also some advanced techniques that we will discuss in the end of this video. And you can add frames at specific position of your robots that you can query later. Also, you can use onshape-to-robot to design fields and environments, not only robots. You can use it, supposed to create the RoboCup soccer field. And also there is some simulation API you can use if you want to play with PyBullet. So this video will have chapters, so don't hesitate to skip directly to the part you are interested in. In the first part, I will talk about how to get started, so how to start using onshape-to-robots, how to install it and run it for the first time. In the second part, I will talk about design time considerations, so how you can do your assembly properly so that it works with onshape-to-robots. And in the last part, I will sweep all the configuration entries that you can use, especially like how to create pure shape approximation for your model and enhance the collision detection, which it is very important for the simulation. I will start by making an Onshape blank account for this tutorial, and I will use the Onshape for Makers plan. So I will create the very first document, I will just make a simple box, and we will see how we can import this box and onshape-to-robot, because the purpose of this part is mostly to just to install and get it running, and we'll see in the next part how we can add joints. So here I'm just drawing a simple box, extruding. I don't care that much about dimension being okay. Okay, here we go. I have my box, and this is my document. I want to be able to export with onshape-to-robot. So first, I need to put it in an assembly, because onshape-to-robot works with assembly. So I will insert this box in an assembly, just one box in the assembly, and this assembly will be the one that I want to use in onshape-to-robot. So the next part for us is to get an API key to be able to send requests on our Onshape account. So for this, you need to go on this link, dev-portal.onshape.com. The link is given in onshape-to-robot documentation as well. And you will land on this page, so you can accept. And then we will go in the API keys menu and click on the upper right, create new API key, and just tick all the boxes. Then create your API, and you will get this token. So this is the name of the API key and a secret token. This secret token you need to just copy and keep it, because it will not be shown again by Onshape actually. Even if you go back later, it will not be shown on the page, so you will have to create a new one if you don't keep it. So this is the access key, this you will be able to see, and this is the secret. This one you just copy. If you close, you see that the name of our key, like the access key itself, is still there, and the secrets I just kept in my pasteboard. Now we need those keys to be available in environment variables, so you can use your BSHRC or whatever favorite shell is, or you can simply put it in a script that you source. This is what I will do in this video. So suppose I have a keys file, I will just paste this from the documentation and replace my access key by the public access key, and the secret key by the private secret key. And I will just source those variables so that later on they are available for onshape-to-robot actually to use them. So again, I am in a totally blank Python environment, so I created a virtual env for this tutorial. So to install onshape-to-robot, you just run the pip install onshape-to-robot command, and you just wait for it to come. This will bring you the last version of onshape-to-robot and all the dependencies. So it will come with a bunch of commands, starting with onshape-to-robot. So onshape-to-robot being the main script to do the imports, and onshape-to-robot -bullet as a script to just try your robot quickly in Bullet with sliders to control the joints. Clear cache to erase all the cache files used by onshape-to-robot, and edit shape to use pure shape approximation editor, and we will discuss this later on. So to start our imports, we will first create a directory for our robots. We'll call it cube, and we will edit cube /config.json file. And in this file, we will write the configuration that will explain onshape-to-robot how to import the robot from Onshape. The minimum config.json file is given in the documentation, and it's like this. So I will paste this in my config.json. So here you can find the document ID, which is the ID of the document in Onshape, and the output format you expect onshape-to-robot to produce. So document ID will be replaced with the ID of my assembly cube. And if you want to find it, just go back to your assembly and check the URL. on the top of your browser, and this second part of your URL, just after document/something, will be what you want. So for me, it's BBC09, etc. So you just copy this part and paste it in the document ID section of your config.json file. And this is the minimum example we can use. So if I save this file, I can run onshape-to-robot with the cube directory as an argument. And it will automatically open the directory, read the config.json file, and start the import using my API keys. So here we go. I got a warning during the imports. That is because actually my document, my part has no mass. And the reason why it has no mass is because I didn't assign a material to it. So I need to go back to Onshape. To do this, you can simply click on your part, use right click, assign material. So I will assign it whatever material I find, so suppose the first one, and validate. And then I can start the script again, and we should avoid this warning now. And all the imports will be okay to go. So to check how the import went, we can just throw the cube in PyBullets. For this, you can use the onshape-to-robot -bullet. So it's just one command, one word, space cube. And it will automatically start PyBullet simulation where I can find my cube, the cube that I properly imported from Onshape in my PyBullet environment. So this script is actually just loading this URDF file and putting it in PyBullet. That's all it does. So we can see that this first import worked properly. So now we created an Onshape account. We just imported a very simple cube, and we will just jump to the design time consideration, and especially how to make joints imported with Onshape-to-robot system, which is a very ingredient indeed to make a robot. So the first requirement, and I think it's a good practice anyway, is that you split your robots in what here I call components, but anyway, which are just blocks that are jointless, and create a top-level assembly in which you just import those components and connect them with joins. So the top-level assembly is just those components that are instantiated as many times as you need them, and connected with the joints you will use, and nothing else actually. Another thing that is not a requirement of Onshape-to-robot, but I think an important advice is to use mate connectors. In Onshape, you can use those mate connectors. You can click on this button for that purpose. And those mate connectors are like ready-made anchor points that you can use later to connect the parts together. And it will be way much more easy in your top-level assembly to click on those anchors and zoom and try to fiddle to find the proper connector. So in first place, I will create a new assembly, clicking to the plus, create assembly. Here we go. I will push the assembly to the right, and I will rename it robots. So maybe you remember that when we created our configuration JSON file, we had this minimum document with just the document ID and URDF, and we didn't specify the name of the assembly. So by default, Onshape-to-robot will take a random assembly, assuming it's a bad practice, of course. If you just have one assembly, it's not a problem. But if, just like this document, you have several assemblies in the same document, which can sometimes be convenient as well, you can specify the assembly using assembly name entry. So in a similar way as I did before, I will just copy this minimal configuration. I will make a quadruped directory, edit quadruped config.json, and paste it. I will retrieve now my document ID token, which is this token in my URL, and paste it as a document ID. And I will add an assembly name entry, just like you can see in this documentation page, in my config.json. And I will name it robots. So this way, onshape-to-robot will know that the assembly that should be imported is the assembly with the name robot and nothing else. So as I said, now that I created my top-level assembly, I will import my components and connect them together using their joints, their ready-made connectors that I prepared. So I will click on Insert, and in Assemblies, I got all the assemblies of the current documents. I will add one body, one W, one plate block, and one leg. So this is just one leg of my robots. So first I will just fix this plate here so that I'm sure that the body doesn't move. So when I click, there is no problem in moving the whole robots around. So now I can only move those parts that I need to assemble. So the very first joint I'm going to create is between this UW structure and the body. And for this, I will click on Revolute Mate, or the M button on my keyboard. And then I will click on first the mate connector of the child in first place, and then the mate connector of the parent in second place. So as you can see, I am not accurate. I'm just clicking very roughly, and since they are already mate connectors, there is no problem. So in that case, I need to invert this orientation and rotate it by 90 degrees to get it straight, just like I wanted. And I have my very first joint. So this is a joint, but this is not yet, this should not be recognized as degree of freedom for onshape-to-robot. For this, I need to rename this mate to DOF underscore something. So I will call it leg 1 underscore A, because I have not that much creativity for this one. It will be leg 1 joint A, and press enter. So the prefix DOF, like degree of freedom, is very important for onshape-to-robot to know that this is actually a degree of freedom. If you don't use this prefix, it will be just fixed joint actually, and this will be considered as a whole body. So I will do the same for the other joints. First, I will click Revolute Mate, then the child and the parent, and press OK. Again, the child and the parent, and press OK. And I will rename those two other joints, DOF leg 1B and DOF leg 1C. So now you can notice that those joints are free. Even in Onshape itself, you can move your robots, and if you import this using Onshape-to-robot, those will be recognized as joints. So I can start my Onshape-to-robot script on the quadruped project and see how it goes. We can see first that three degrees of freedoms, which are revolutes, are found. And all the parts are being imported one by one subsequently. At the end of the imports, again, we can use onshape-to-robot bullet on the quadruped project. And we can see that our first leg was imported in Onshape. And we can just use the sliders that automatically appears on the right to play with the robots and to do some experiments with the robots to see how it goes. So I can now add the other legs on my robots in a similar way. So I will insert the missing parts. And connect them using my Revolute Mate. So you can see that this is quite fast process. Once you created all the components of your robots themselves, the top level assembly is not very long actually to do, because it's just about connecting the parts together using those Revolute Mates. So here we go. So now I have all my joints. I created all my joints, I gave them proper name, and as you can see, it is not always properly aligned like I want them to be. So if I import this using onshape-to-robot, onshape-to-robot will just use my robots know this snapshot of the robot as the 0 position. So it's not good, definitely. One easy way to be sure that the 0 are okay is to create constraints that you just suppress afterhand. So for instance, you can use simply parallel mate just to achieve this in this particular case, but maybe it will depend on your robots. So I do now have 12 parallel constraints that are just constraining my robots. My robot can't move anymore. And I can simply suppress them. Suppress means they are not active, but they are still present in the documents to be re-enabled again. So if I move my robot, I can just play with my robot to check how it moves. And if I want to go back to the 0, I can just unsuppress those parallel constraints and suppress them again if I want to be able to move it. Now that I'm pretty sure of this position, I can also snapshot it. For this, you can use the named position on the top right, and you can name this position 0 and click the plus button, and then you will be able to go back to this position later on by simply going back in this menu. So again, if I move my robot like this and I go back in named position, I can select the position 0 and my joints will go back to this 0 position. So even I don't need those parallel constraints anymore because I just built this 0 position. I can now import this robot using onshape-to-robot again, just to check that everything is all right. So the import didn't take any longer than before because every part were in the cache actually. onshape-to-robot keeps some cache to avoid sending a lot of API requests, especially when you iterate, when you just change a little thing, you don't want 1,000 requests to go on again. And no, I didn't create parts, I just imported parts that were already existing. So it was almost instantaneous. So I will start onshape-to-robot quadruped, and here we are getting the full quadruped robots, and we can use all the joints. And we see that the 0 is the proper 0 I wanted to have in my simulation. So now we will discuss the pure shape approximation problem. So we have a robot. This is the quadruped that we assembled and imported using onshape-to-robots, and we can use onshape-to-robot bullets to simulate it. And as you can notice, this is functioning. The robot can be simulated like that because SpyBullet can use meshes for simulation. But this is very computational. Using meshes is not what you want to do, especially if you want to do a lot of computation, like suppose reinforcement learning or such tasks. So you might want to use instead pure shapes to approximate those shapes by simple shape like boxes or spheres. To do this, onshape-to-robot provides two solutions. The first one is to manually approximate the shape using OpenScad, and the second one is to use pure shape sketches. So we will see how both are working. So the first solution onshape-to-robot provides you for pure shape approximation is to write your own pure shape using SCAD files. So quadruped directory. In this directory, you can see the config.json file, the one we wrote to explain how to import our robot. STL files as well, that are the meshes that were imported during the generation, and those were provided by Onshape API. And those files actually contain just the raw meshes, and the part files are internal metadata used by onshape-to-robot. So you can use the command onshape-to-robot edit shape and give it any STL file, so quadruped/leg.stl, this will open you such a window. So this is OpenScad software, and of course you need OpenScad installed so you can get this working. You can see the STL on the right in like low opacity, and on the left, classical OpenScad code menu. So if you are familiar with OpenScad, you can write any OpenScad code you like on the left. It can only be union of cubes, cylinders, or spheres, and the output of this file will actually be the pure shape that will be issued in your URDF file. So this is a tedious process because you need to write yourself all the primitives. For instance, I can uncomment a sphere that will appear here and translate it by something like 80 millimeters downward, maybe 100, and I will get it at the tip of my leg. So like this, I'm doing myself the work of approximation, and I am approximating this whole leg by just a sphere at the tip. Maybe it is enough for my simulation to run, suppose. So now, to get it working, I need to edit my quadruped config.json and to set use scads to true in first place, and to start again the import. So onshape-to-robot quadruped. And doing this, onshape-to-robot will just run the OpenScad script I wrote and use it for the collision part of the URDF, which will be different from the render part. So again, if I start bullet quadruped, I can't see any difference in this view, but if I press the button W, I can now see that my legs are just in the collision world approximated with simple spheres. So I can't see this in this view, of course, because it will look quite similar, except if I have a collision here, it will go through the leg. But in the collision world, it is now just approximated with simple spheres. As I said, using OpenScad to write your pure shape can be very tedious. So we propose you another solution that is way much easier, and this is what we call pure sketches, but it requires some steps to follow. So first, you will edit the parts. So I will click on Open Linked Documents to open the documents where my leg is actually drawn, and I will edit it, and I will create a sketch that will always remain a sketch on the tip of my leg. And on this sketch, I will just draw a rectangle that is exactly the rectangle of the tip. And then I will rename this sketch Pure Shapes space 3. The 3 here is the number of millimeters, so we want to extrude this. And Pure Shapes is just a marker, it's just a name, so that onshape-to-robot is able to know that this is a pure sketch. The idea behind the pure sketch is that the pure sketch can be analyzed by onshape-to-robot so that the pure shape can be introduced in the URDF files finally, because there is no way using the meshes or the other sketch to know what we want to use. So the pure shape 3 here means that this sketch is the pure shape, that it will be extruded as a box here in the final URDF. It will be a pure box with a thickness of 3. So I will do the same for the other parts. I will do another sketch here using this rectangle again, and I will call it as well Pure Shapes 3. And again here, suppose I want just the tip of my leg. Here we go, and now we have 3 pure sketches. So you can hide them, it's not an issue. If you don't want them to bother you, you can hide them. And now I'm going to create a new version of this leg. And I'm going to update my leg in my main assembly by clicking here and here. Once this is done, there are just two things to do. The first one is to start onshape-to-robot import again, so that everything refreshes and the reference to the document refreshes. I need just to start the import again. And you can use the command onshape-to-robot pure sketch on the part you want. So onshape-to-robot pure sketch quadruped leg.stl. And this is where onshape-to-robot is going to query automatically the part file and retrieve the pure sketches. And here you go, you see that those boxes are already made for you. And they are perfectly matching my parts, as the tip of my leg here is automatically created just using pure cubes in the OpenScad files on the left. So you can just save the SCAD files now. Actually, it is just showing you the SCAD file so that you can have a visual check if there are no mistakes. And if you start the import again with the useCAD flag to true, these pure shapes will be used instead of the sphere we had before. So I start the import again for a second time. And now I will use my quadruped in PyBullet. Again, I see no difference in this view, but if I press the W button, I can see that now my legs are approximated with just 3 cubes at the tip. That are the cubes that I extruded using this pure sketch trick. Sometimes the robot can become more and more complex and the render can take a lot of time. So for this, we strongly recommend that you use the drawCollision flag. The drawCollision flag that you can edit in your JSON as drawCollision true is quite useful for both debugging your collision and lightening the load time of your robots. Actually, the effect of this flag is that the visual section of your URDF this time will be exactly the same as the collision section. So whatever onshape-to-robot is outputting usually in the collision section, it will be outputted the same in the visual section. So if I use this flag to true and start the import again, and then load it in PyBullet, you can see this time that even the visual now are the same as collision. So I can't see my legs, my full legs anymore, because those 3 cubes are also in the visual section. And this is getting the robots loaded way much faster. And if you don't need a very fancy visualization of your robots, I strongly recommend that you pass this flag to true. Of course, this only has positive effects if you did the proper pure shape approximation on your raw robot. Another common concern is to be able to track any particular frame on your robot. So you want to be able to tag a particular frame somewhere and be able to access it, to programmatically access it later on. So back to my quadruped, I will simply click Insert and go to Other Documents, select my frame, and insert my frame assembly anywhere in my document. And now I'm going to fasten this frame to anything I want to track, to be able to track in my robot. So of course there can be multiple frames, as much as you want. You can use fastened mate. Just click on the child first, always, as usual, just for the joint. And the parent will be, suppose, the body here, if I want to track, to be able to track my body. So again, this frame can be any kind of assembly. It can be any kind of assembly. Here it's more like it's better to have something visual because you can see the x-axis, the y-axis, the z-axis clearly. And so you can clearly see the frame. The only thing I need to do is to rename this to frame underscore something, where something is the name of my frame. Like I can call it center, because it's the center of my robots, and I will be able to track this particular frame. Now I'm going to import again my robot using onshape-to-robot quadruped. So my frame will be added to my URDF as a dummy link connection actually. And if you want to check that it worked, you simply just start bullet again. You should see in background in the terminal the position of the frame. So you can see here center frame appearing, which is the position of the frame that is being tracked. And if I move, you see that the frame is moving above in the debug window. So I'm tracking now the frame that is the middle of my robots. And of course, the frame is a full transformation matrix. You can get the roll, the pitch, and the yaw as well. So as your robot is going to be more and more detailed in your assembly, you can include screws, nuts, or even wires, and it can become very, very big actually. And maybe you don't want to include all those parts in your URDF files because in the collision or visual world, it doesn't make any sense to have them. So in onshape-to-robot, there are two ways to achieve this, to reduce the number of parts that you import because they are useless. The first way is to use the ignore flag. That is just a list of things that will be ignored during the import. The second solution is to use whitelist. Whitelist is a list of the only items that will be imported. So if the whitelist is not specified, of course, all the items will be imported. But as long as you specify a whitelist, only the item on the whitelist will be imported. So let's see how it works in practice. On my quadruped, suppose I want to ignore those use shapes. So suppose those parts doesn't make that much sense for me because I don't care about them colliding. Those are just computationally expensive, so I want to remove them. In this case, I will just edit my config.json file, and I can add the ignore section with the U, which is the name of the part in Onshape this entry. And then I will start my import again. And this time, you will see actually during the import this comment. It means that this part is being ignored in the visual and collision world. It doesn't mean that it is being ignored in the dynamics computation. So the mass, the center of mass, the inertia are still used. So that is why requests are still sent, but the meshes are not retrieved, and there will be no entry in the visual and collision of your file. So if I now check it out, I can see my robot is now appearing without those U shape parts. So you can think of this being a convenient way to ignore some small parts like screws or nuts. Another way to ignore some parts is to do the opposite and to use whitelist. And for this, you can edit your config.json file and instead of ignore, use a whitelist. In the whitelist, I can include the only parts I want to be present in my robot. Suppose I want the body and the leg. And those will be the only parts. So those are just part names that will be matched and kept in the import. And as you can see during the import, almost everything is being ignored. And if I start my robot in bullet this time, only the body and the leg were kept for the collision and the visual world. So again, doesn't mean that the dynamics is not good. The dynamics is computed exactly the same way. Only the leg and body is kept for the rendering and the collision. Thank you for watching this video. I hope it will help you in your robotics project. If you have any issue, do not hesitate to go on the official GitHub repository. So it's simply roban/onshape-to-robot and open an issue and we can start discussing your problem here. This is still an ongoing development project. There are still feature requests and work in progress. And I hope we can work together to improve this project.